Hello, class. I am doing the next in the series of lectures here on shear force and bending moment diagrams. And this one, the first thing that I wanted to do in this lecture, and that's why I actually drew this in, is the last lecture that I did. I sort of ended it with a preface that we were going to work on cantilever beams, and I drew. I was at the thing. I was like, God, that doesn't seem right. R sub A, and I remember drawing R sub A like down from below and going up to 0, and then coming over here and then going down or whatever, and that just didn't seem right to me. And so after I finished that lecture, I looked back in my notes. And I realized that, no, of course not. That's not right, because this is a positive slope, right? It's positive. How do I know that? Because this slope here is positive, isn't it, for my bending moment diagram? It's a different color, supposedly. Yeah, maybe my computer's not picking up. So that's right. So if the slope down here is positive up and to the right, then this has to be a positive area here too, so that it can integrate into a positive slope down here. And of course, that's how it works. And not only that, what I'd like to do, I'm going to put that blue pen away, is let's just cut this. Let's just cut that right there and see what type of forces we have on that, using the other method that we have, which is the Ruck Leduc method. Up, right hand, clockwise, right? So if we just look at that, what do we really have on that? Now we've got P pushing down, don't we? And over here we have V going up. So we know that V plus P equals 0, or V equals minus P. Wait a second. What? Yeah, that's a, oh, wait. Oh, oh my God, I should just restart this lecture, I think. Of course it's not, it's V minus P. I can fix that one without using correct type. So that's plus, of course, because P is going down, so it's minus, and V, let me just draw V in on this side. That's where we're doing the summation of forces. So that's what we've got, summation of forces of Y. Let's give that an actual, I'll call that A, at point A, equal to 0, tells us that it's V minus P equals 0, and so V equals plus P, and that's of course what we've got here, because what are we really doing? We're going up R sub A. I think we made P 1,000 newtons, as I remember, so we could say that this right here is 1,000 newtons, and we're going up R sub A. This distance right here would be R sub A, and then we're coming down P, right? Back to 0, and then it's 0 for the rest of the way out there. I'm going to look at other cantilever problems too, but what I want to do is I want to look at this so that sorry, just going to box that out. Look at this because later on we're going to come back to a cantilever problem. But what I want to also look at now is uniform distributed loads. And I'm going to look at a complex beam first. The first, sort of just to go over, this is a little more complex loading than the complex beam that we had before. So let me just give you the things. So let's see, 2.5, 5.5, 7.5. So I will draw the beam. There we go. There's our beam. Oops, sorry. And then the beam is going to be, it's a complex loading, so it's 2.5 in is going to be my support. I'm going to have a force that's going down on the end at 20 kilonewtons, right? So my first support here, I'm going to call that B. So this will be R sub B. That's my reactionary force that's holding this beam up. And then another 3, so it'd be 1, 2, 3. I'm going to have another force of 40 kilonewtons pushing down. And then at the end, I'm going to have my other support, which I'm going to call R sub D. All right. I'm not sure why I originally called them that, but at the time, I'm sure it seemed like a good idea. Now, the first thing we want to do, remember, and that's why we always use quadrille paper, because that's right, we're engineers. Now, let's put down different things, because all of it in our shear force and bending moment diagrams, these are going to be critical location for direction changes in our thing. And what we can do is at the end, of course, we can just draw a nice thick line there. I don't know where we're going with that, but that's going to be V. And with this, I'm going to put the thing right in the center, because what you're going to see is that we're going to have positive and negative. So that's my shear force diagram, positive and negative for my shear force. And then I want a bending moment diagram down here too. And I'm going to put the bending moment diagram right here, because what you're going to see is we're going to have a little more negative than positive for our bending moment diagram. So I'm going to put that down there. And what we're going to do is we're going to take the loading, we're going to look at the loading, we're going to figure out what the loading is using our summation of forces in the y direction equal to 0 first, right? So we can do that. I've got 20 kilonewtons. I'm just going to put an arrow here. We're all intelligent human beings. I think everybody can see that we've got 20 and 40, so that's 60. And we've got R sub B and R sub D. So we've got R sub B plus R sub D equals 60 kilonewtons, right? Now what we have to do is we have to figure out, so we're going to sum forces about R sub D. Could we sum forces about R sub B, moments about R sub B? I said forces, but I meant moments. Yes, of course we could. R sub D, yeah, it just seems easier. So everything over there is going one way or the other. It's easy to take the distances. And in fact, I forgot to give you the distances, even though it's to scale. So this is going to be 2.5 meters. This is going to be 3 meters. And this is going to be 2 meters. All right? So you can see the distances between the individual forces that we have there. So if I was to sum the moments about D, let's go to the very end first. Well, that's going to be a positive moment, isn't it? So that's going to be 20 kilonewtons. That's a 2. Take my word for it. Times 2, 3, 2.5. So that gives me 7.5 meters. And then the next one, that's going to be R sub B, and that's going to be a minus, because that's tending to turn it clockwise about that position, isn't it? So that's going to be R sub B, I'll just leave R sub B, times 5 meters, right? We all know it's R sub B. Okay, and then plus, because it's got a 40 kilonewtons and it's going to be going around that way, plus 40 kilonewtons times 2 meters. And so what that does is that immediately gives us R sub B, doesn't it? What the force, or did I say B? I meant D. So I'm in the force around. Oh, wait a second. I'm crossing it out. B. R sub B, of course, because I've got R sub B. This is what I've got. So R sub B is going to be equal to 20 times 75. Excuse me, and I'm working in kilonewtons here, so I'm going to actually use kilonewtons in my calculations. I know you're thinking, well, it's taking you a long time. You got to punch in 3 more zeros there or whatever, right? Times 7.5. No, that's the way you do it. Or you put in 20 times 10 to the 3. You want to work in newtons whenever you work with your calculator. Your calculator hates you, right? So if you try to screw with it, it will be bad. So plus 40 kilonewtons times 2 meters. All right. And that gives me 230 kilonewton meters. So I've got 230 kilonewton meters. Now, of course, it didn't come out as kilonewton. It came out as 230 times 10 to the 3 newton meters, right? So, but that's fine. And then I'm going to divide that by the 5 meters that I've got here to get me R sub B. And that gives me 46 kilonewtons. Well, if R sub B is 46 kilonewtons, then R sub D has got to be 14 kilonewtons. Sorry, it took me a second there. You guys are younger than me. I had to do the 60 minus 26 in my head there for a second, even though I've got it written right here in my notes. I don't look at my notes all the time. I try to, anything I can do, I just like I do in class, try to do, on the board here. Okay, so we've got really everything that we need now to do this problem, because we've got minus 20 kilonewtons. I'm going to say that this is 20 kilonewtons. Yeah, I think that should work out. So minus 20 kilonewtons. I'll just use one thing there until we get over here. And then what happens at R sub B? Well, at R sub B, we go up 46 kilonewtons, don't we? So we're going up 46 kilonewtons. I'll draw that, right? So that is 46 kilonewtons that we go up. That's a 4 and a 6. I hope everybody can see that. So we're going down 20. That's the 20 that we are at the end. And so we're down 20. This is minus 20. And then we go up 46. So that brings us up to positive 26 plus 26 kilonewtons, right? Does everybody see that? Then we're going down 40. So we're going to go down to minus 14. And then we're going to go all the way over to R sub D, and we're going to go back up the 14 to 0. So we start at 0, we go down 20, right? Minus 20. And then we go up 46. I should put like a little squiggly line there. And then we're at 26 plus 26. And then we go down to minus 14, and we're across minus 14, and then we go up 14 back to 0. And that's our shear force diagram. And at any point, we can tell exactly where we are and what we're doing. I'm just going to crosshatch that so that everybody can see. I think I'll use orange. I know you colorblind guys are going, he says orange, but it's brown. No, it's it supposedly is orange. And actually looking on my screen now, it looks more brown than orange. All right, so there we go. And now that we have that, we can figure out what the bending moment diagram is going to be. And I now realize that I probably should have put the bending moment diagram a little bit lower so that we would have more And because I have this and I don't have to write over it, I can just do that. So I'm going to give myself a little more room with the bending moment diagram, and I'm going to move it down here. And then I'm going to extend this down a little ways so that we have plenty of room, and hopefully that'll dry in time. So it should be no problem. All right. Now, what is the bending moment diagram? How are we going to figure this out? Because right now, what it's telling me, we know that on a complex beam, I've got to begin and end at 0. Boy, that's not good. I'm going to go with it. So we know we begin and end on 0. We know that the first thing we're going to do is we're going to go down minus 20. That's minus 20 kilonewtons. But it's really for the slope down here because we're integrating this into this. The slope down here will be minus 20 kilonewton meters per meter. And we're going 2.5 meters. 2.5 meters. Let's do that. 2.5 meters times minus 20 kilonewton meters per meter equals, right, minus 50 kilonewton meters. Does everyone see that? So that's where I've got to go down here. I'm going to go down to minus 50. Let's just drop that down. So right at this point, I'm at minus 50. Let's say that that is, let's see, 50. I'll break it up into 225s. There you go. Now, how do I get there? Well, this is a constant, isn't it? This was 0 here, and it's become, if I integrate 0, it becomes a constant. If I integrate the constant, it becomes Cx, doesn't it? Right, it becomes Cx. So Cx, what does Cx look like? Right, well, let's just look at it. Let's integrate some things. So here's 0. So if I integrate 0, I get a constant, right? Let's use another line, another pen. So if I integrate, so this going down is an integration, I get a constant, right? I'm using red. And then if I integrate that, I get a straight line, or a polynomial of degree 1. If I integrate that, I get a parabolic spandrel, right? If I integrate that, I get a cubic spandrel, right? So 0, constant, Cx, Cx squared, C1, C2, C3, I don't know, whatever. And then C4x cubed. So, you can see how it integrates all the way up. And so we're just doing an easy one here. This is just integration from a constant to a straight line. And we know that this is going to be minus 50 kilonewton meters, right? Now, how about at this next point here? What is it going to be there? Well, we can do this one of two ways. We can say, okay, well, we've got 26. This is positive, right? That's positive. That's negative. That's negative. So we know that this positive now is going to be 26 times 3. So that's 78. Minus 50 plus 78. Minus 50 plus 78 would bring us to 28, wouldn't it? Plus 28 kilonewton meters. Now, let's just check this. You know, this is minus 14, isn't it? Minus 14 times 2. Minus 14 times 2 is minus 28. So 28 minus 28 brings us back to 0. And how do we get to these? Well, this is a constant, so it's got to be a straight line. And this is a constant, so it's got to be a straight line too. Right? Does everyone see how that works? Now, where is this beam going to break, if it's going to break anywhere? I should use the green. If it's going to break in shear, it's going to break right here. Things don't usually break in shear, but it would break right in the middle there if it breaks in shear. So shear, not a very good pen. And if it breaks by a bending moment, it's going to break right here. Right, so this is if it breaks by a bending moment, or if it breaks by normal. Shear, of course, would be, that would be the symbol for shear. So yeah, that point there is a point that we really have to focus on in our design, isn't it? Right, of this, you know, member that's going to take that type of loading. All right, I just thought I'd point that out to you because this is a complex beam. I wanted to show you a complex beam, how we work through this. There's really getting the procedure down. Then we work through this thing. But what we want to do now is we want to work through another cantilever beam problem. Let me just see if I've got enough room here. It's not looking real good, but who knows? And, you know, why did I draw that there? Because now I've got a big blank space here. Let's see. Oh, yeah, we've got enough time to get into those couple areas. All right. I wanted to look at a simple beam with some non-uniform loading. Still point loads, but also non-uniform loading. And I think that I can do that here by putting my diagrams here. And so I'm going to put the actual loading diagram here. Again, like I say, this is just, so this would be 7. Let's see, 1, 2, 3, 4, 5, 6, 7. Oh, that's perfect. So this is my beam, and it's simply supported at both ends. So I'm just going to drop my, you know, lines down here for my shear force diagram and bending moment diagram. I haven't even shown you what the loading is, and you're already chomping at the bit to solve the problem. Isn't that fantastic? So I've got 1 meter in is going to be 10 kilonewtons. Now I'm just going to put 10K there, but I think everybody knows what that is. And then 1 meter in from this end is going to be 12 kilonewtons, right? However, in the middle, I'm going to have a distributed load that goes from 2 kilonewtons in all the way to 2 kilonewtons, or from 2 meters in all the way to 2 meters at this end too. And this is a uniformly distributed load. In other words, we're piling a bunch of sandbags up here, and the sandbags are all the same height. They're all the same weight. They're all the same height. It's a uniformly distributed load. I thought uniform, yeah, I think uniformly really is better. Uniformly, now I have no idea what that looks like. Uniformly distributed load is probably better than uniform distributed load. I wasn't sure which way I wanted to go with that. Now, let's drop some of these lines down that are going to be critical for our shear force and bending moment diagrams too, and you can see that there's a lot of them. The reason that I wanted to look at this uniformly distributed load is because this really enters in a more realistic way to how, you know, beams are loaded. A lot of the loading in a beam um, isn't somebody stacking a refrigerator in one part of the floor or something like that. You know, it's really the building materials. And so the building materials, you know, are in some ways uniformly distributed over the load. And that's what we'd want to look at. So I've got going to go with I'll put V here because it's a pretty good size, and I can put plus and minuses on both sides, so it's pretty good. That's V. Just going to put that there. I probably shouldn't, but I'm going to. All right, because I'm going to draw the thing in another color anyway. Let's see what we can do. We can go with blue maybe. There's a bright blue here. I hope that works. Actually, that blue up there didn't do too badly either. I have no idea. We'll try either one. Now, first of all, we've got the two supports here at the two ends. And I'm going to say that those are R sub A and R sub B. Oh, I forgot to give you the loading for this distributed load, by the way. This is going to be 5 kilonewtons per meter. 5 kilonewtons per meter. Let me circle that because that is what we're really looking at in this whole example, right? How am I going to handle that 5 kilonewtons per meter? Not only that, I also want to put in there the distances, because each one of these, you can tell, I use quadrille paper, so you can see the grid underneath it, but still, I might as well number these. So that's 1, that's 3 meters between those. That's 1, and that's 1. All right. So of course, the first thing that we want to do is we want to sum the forces in the y direction so that we can figure out what this is. And I think everybody can see, well, like, I'm not, actually, I want to talk about the distributed load for a second but everybody can see that it's R sub A plus R sub B, right, is going to equal what the forces are up here. Now, 10 kilonewtons plus 12 kilonewtons, well, that's 22 kilonewtons. That's easy. Those are point loads. We just add those together. Now, what you do here when you're summing up the loads and when you're doing the moments too, because we're going to have to sum the moments, and that's what this is all about. How much force is here? Well, 5 kilonewtons per meter over 3 meters, right? So wouldn't that be 15 kilonewtons? So when I'm summing the forces, that's all I need to know. I just need to know how much really is pushing down. 5 kilonewtons per meter, 3 meters, 15 kilonewtons. 15 plus 10, 25, plus 12, 37. So 37 kilonewtons. That's all I need for that first equation. But how about summation of moments, right? Now I want to get rid of R sub A or R sub B. So I could do it either way, couldn't I? I could look at R sub B and then, you know, subtract off and everything else. But I think that's what I'll do. I'll sum the moments about B. So if I'm summing the moments about B, I don't have to worry about R sub B at all. I just have to worry about R sub A, and that's causing a negative moment, which would be R sub A, and then times 1, 2, 3, 4, 7 meters. And then the next one is a positive moment, because that would be the 10 kilonewtons times 6 meters. So I've got 10 kilonewtons times 6 meters. That is a 10. And then the next one that I have is the 12 kilonewtons times 1 meter. That's a positive also, 12 kilonewtons times 1 meter. And the last positive one I have is that 5 kilonewtons per meter. But where do I put that? You know, it's uniform. It's uniform. Uniformly distributed load total. So let's say, you know, P total applied at, I know I'm keeping it like, you know, yeah, centroid. There's that centroid thing popping up again. Centroid. Oh my God. Once again, we have to apply this at the centroid. That centroid, we've always got to find the centroid of things. Whether it's uniformly or not, we have to put it at the centroid. So we're going to use non-uniformly ones. But at the centroid, it's pretty easy, isn't it? It's right in the middle here. 1.5 from either. So I'm going to have to actually drop something down here. You know, well, no, not actually, I don't have to drop it down there. What am I doing? I'm not going to drop that down there, because this is where we're applying it. I mean, we are going to see that something actually occurs right at that location. Okay, I'm getting ahead of myself. You know, what I'll do is I'll drop it down. You know, I'm sort of letting the cat out of the bag, but I'm going to drop it down here with an orange, because we're going to need that later on. Now, where's that? That's right in the, let's see, that'd be right in the middle of this, all the way down. We'll need that later on. I've sort of given you the punchline even before I've solved the entire problem, but let's just look at what we've got there. All right. First of all, we know what R sub A, or we're going to, let's finish this one now. So I've still got this last positive. You know, I should put this one down here. The last positive one, and that's going to be 15, right? So we mass the whole 15 kilonewtons right at the centroid. So that's going to be 15 kilonewtons, right? Times, how far is that centroid from there now? That's 1, 2, and 1.5. So that's 3.5 meters. I had to jump a little bit into my, you know, series of integrations. Integrate. You know, integrate all the way down. And of course, what we would have here is we would have a quartic after that. So anyway, we're down there, and we've actually sliced into their piece of the pie. But anyway, we've got that all set up now. I should get rid of this plus sign. I don't know why I've should have done that. Would have dried it by already. Okay, now, so let's look at what R sub A is. Don't have a lot of room. We'll probably finish this up on the next page, but R sub A is going to be 60 plus 12 plus 3.5 times 15. Well, I have no idea what that is. Let's see, 3.5 times 15. 52.5. Who would know that? So 52.5 kilonewton meters plus 60 kilonewton meters plus 12 kilonewton meters. I don't just want to, you know, write these all down, right? Because, and I had the room anyway. Although, yes, thank you for reminding me that I actually should separate those out for your notes so that you know that that equation above and the equation below are two totally different equations. But I still had enough room, and I can divide this now by the 7 meters that I have to end up getting R sub A. Oh, there's the alarm too. All right, so we'll finish this up later, but R sub A then, and we'll know R sub B too, is going to be 112.5, 124.5, and you're all saying, no, that's wrong. 124.5 divided by 7 is 17.786. Let's say 9. 17.79. 17.79 kilonewtons. Is that what I got? Let's just make, yep, that's exactly what I got. In fact, I rounded it to 17.78 because I wasn't as good of an engineer then as I am today. And that also tells us that R sub B, that's an R, is going to equal 19.2. Let me just subtract 37, and I get 19.2. Actually, 19.21 to be exact, kilonewtons. So there you go. There's R sub B and there's R sub A, and we can then use those as we start to put this together. In fact, we could actually, do this right now and finish this off. It'll only take a minute. So the first thing we're going to do is we're going to go up R sub A. So that is going to be 17. Let's just say that that right there is the 17.8. 17.8, that's R sub A. And then I go across. Now I go down 10. So now I'm at 7.8, right? Until I go across here. So that's 7.8. Now this is going to take me down. It's going to take me down 15. So 7.8 minus 15. 7.8 minus 15 equals minus 7.2. So I'm going to go down to minus 7.2, minus 7.2. Oh, wait. Sorry about that. Oh, thank God I do have the correct pen. I'm not going down there. I'm going down way over on the other side of the thing here, right? So this is where I'm going to get down to minus 7.2. In fact, I'll just put a little line there. And this is where I'm going to start. How am I going there? It's a constant, right? It's a constant as far as the distribution goes. So this has got to be a straight line. That's a constant. It's negative. This is a negative going straight line, right? So I'm all fine. Then positive over there. I'm at minus 7.2. I go down to minus 19.2 over and back up to 0, right? Because R sub B equals 19.2 kilonewtons, doesn't it? So I'm going down, right? 7.2 minus 12 minus 19.2 right there. Right here, I'm at minus 7.2. How did I get there? Right? So look at that. That is, I'm going to color that green. That is our shear force diagram for what we want to do now for the bending moment diagram, which is going to be right below that. So for one, we go up 17.8, don't we? Right? I think I'm just gonna draw this down here. So I have no idea how that got there. So for one, we've got a positive slope here. So we're going up 17.8. There you go. So we've gone up to 17.8. I should probably have an even better pen for that. Now we've got a lower slope here, 7.8, right? So we go up at a high slope of 17.8, then we go at a slower slope of 7.8, then we're going to go constant till we get to this point right here where we have zero slope. And it's going to be parabolic, isn't it? And it's going to be inverted parabolic because we start large and go to zero. Then we go to zero, we go negative. So at that next point, we should be going like that. Then we go small, just like we did before, and then large. And we know that this right here is going to be at 19.2 kilonewton meters, right? Because that's one. And then that's 7.2 per meter. And so we can figure out what that is, because 19.2 plus 7.2 is 26.4, right? And then over here, this one went up to 17.8 times 1, right? Plus 7.8. 17.8 plus 7.8 is 25.6. Right? But what is that right in the middle? Well, 25.6. Let's look at this right here. Right? Isn't that a triangle? Isn't that a triangle that looks like this? 7.8. And we want to find out this distance right here, don't we? Well, it's 15 that goes through there, and it's in 3, so we got to divide it by 3. So 7.8 down to 7.2. Where is that going to cross? It's not going to cross right in the middle, is it? No, it's going to cross at 7.8 fifteenths, or 78 1/50ths of the distance of the 3 meters. So let's just do that now. Let's go 78 divided by 150 times 3 meters is 1.56. 1.56 meters right here. 1.56 times 7.8. That gives me 12.17, right? So we know it's 12.17 high, or 12.2. So that's going to be 37.8. Wait, is that right? 25.6. Wait, that's not right. 30. That's not going to be. No, it's going to be 6.1. How did I get that? 3 meters, just a second, 15. Oh, it's 1/2. I'm sorry. So divided by 2, 6.1. That's not. Thank God I only wrote one. So 6.1. I had, it's a triangle. It's a triangle, so I had to divide it by 2. Okay, so 6.1. So that gives me 31.7. So that's our max is going to be 31.7 kilonewton meters. All right. And then we know what our maximum is here. It's minus 19.2. All right. See you at the next lecture.